Hi, and welcome to the Foundations course Lesson 7, Modeling Basics, Part C on Logistic Regression. In the last lesson, we looked at modeling continuous outcomes with linear regression models, but now we're going to look at how to model binary categorical outcomes using logistic regression models. The familiar overview table tells us that we have to use a link function. And for that link function, we use the log odds of the outcome or event. And we are measuring the effect of different variables with an odds ratio. And that effect is not any longer additive, but multiplicative. So we're working with categorical data now, more specifically binary categorical data, where we either observe an outcome or event or we don't. And you probably remember this table with the different risk measures. Well, what we're most interested in now is the odds ratio that we can determine by dividing A with B and then C with D to determine the positive odds in group 1 and group 2 respectively, and the odds ratio is the ratio of positive outcome odds in both groups. So if the odds ratio is larger than 1, then that means that the odds in group 1, which is usually the exposed group or the experimental group, is larger than that in group 2, which is the unexposed group or the control group. And as you can see, the calculations of relative risk and odds ratio are completely different, because odds ratios, as the name implies, do not work with probabilities but with odds. And the interesting thing is that probabilities are confined by the value 1. They can never exceed that value, whereas odds can definitely exceed the value 1. And this has implications for the interpretation of odds ratios. The basic rule is that the odds ratio is always further away from 1 than the relative risk. And if the relative risk is larger than 1, then that means that the odds ratio will be larger than the relative risk. Whereas if the relative risk is smaller than 1, odds ratio will be smaller than the relative risk. And in rare outcomes, the odds ratio is a pretty good indicator of the relative risk. So there won't be significant differences between those two risk measures. However, in more common outcomes, the probability or risk in the unexposed group will be higher, resulting in much higher odds ratios than their relative risk, counterparts, or in other words, the odds ratio overestimates the relative risk. And it's not a clear-cut definition what a low probability risk is, but it has been suggested based on the mathematical relationship between odds ratios and relative risk that you should use 10% as a cutoff for low versus high probabilities in the unexposed group. Now, it's definitely important to be aware of this difference. However, in many studies, you will be using a logistic regression analysis, which yields odds ratios instead of relative risk measures. Thus, you should be more cautious about stating the effect size with certainty when you have found a relatively large odds ratio in a study with a high risk in the unexposed group. And providing 95% confidence intervals for the odds ratio definitely helps with this. And there are ways to estimate the relative risk measure from an odds ratio with the formula as stated here. It's not a perfect formula, but it works pretty well. And there are also more advanced techniques to estimate the relative risk measure. All right, now that we've highlighted this point, we can move on to logistic regression models. And in logistic regression models, we try to model a binary categorical outcome. And we do that by using the link function log odds, and that's also which is sometimes also called logit. and our equation becomes the log odds of the disease or a certain outcome or event is the logit of probability, and that's the same as the log of the probability of an event divided by the non-probability of the event, is beta 0 plus beta 1 times x1 plus beta 2 times x2 and so on with all the additional variables in the model, plus e as our residual term. Now, as the measure of the effect of variables in the model, we use the odds ratio. And because we use a ratio, the effect of the variables is multiplicative. If we want to test for significance of single parameters in the model, we use a wall test, which is based on either the z or chi-square statistic, or a score test, which is based on the chi-square statistic. Now, if we want to test the entire model, we can use the likelihood ratio test, also based on the chi-square statistic, and the AIC value. Model fit or performance is usually expressed in terms of the area under the curve value, and that's also called the C-index. Now, that use of the ling function may be a little bit confusing, but it's not that complicated. So what we actually model is the log odds of the disease, but our statistical software will give us regression coefficients in the form of a linear equation beta 0 plus beta 1 times x1. And in the context of the log odds of the disease, that means the log of the baseline odds plus the log of the odds ratio. Well, that's all nice and all, but our minds struggle with the concept of logarithmic terms. So we want to go from the log odds of the disease towards the odds of the disease. And we do that in the two groups separately, the odds in the unexposed group and the odds in the exposed group. In the unexposed group, where x1 has the value 0, the beta 1 term gets eliminated from the equation, so that we only work with the beta 0 term. And to go from a logarithmic term to a non-logarithmic term, we need to take the inverse of the logarithm or the anti-log. And we do that by taking the exponent of the regression coefficient beta 0, and that gives us the baseline odds. Now, in the exposed group, x1 has the value 1, so we need to take into account the beta 0 and the beta 1 term. And here we take the product of the exponent of beta 0 and the exponent of beta 1, and that is the equivalent of the baseline odds multiplied by the odds ratio. Now you probably understand much better why the odds ratio has a multiplicative effect instead of an additive effect. This is an example of a standard output by a statistical software package on a logistic regression model. And in this example, we only use one categorical variable x1. So we have the equation log odds of the disease or outcome is the logit of a probability is beta 0 plus beta 1 times x1. And we get two different parameters from our model output. The first parameter is the constant x0 or beta 0. And this is slightly different from the intercept in linear regression because it does not give us the baseline odds, but it's the log baseline odds. And we also get the baseline odds under the column exponent of the regression coefficient beta. And in addition to that, we also get a standard error for beta 0 and the z value, which is calculated by beta 0 divided by its standard error. and then the p-value for the Wald test. And of course, again, the null hypothesis for the p-values is that the regression coefficient beta 0 and or beta 1 are 0, and the alternative hypothesis is that they are not 0. Now, as the second parameter, we get the categorical variable 1 x1 with beta 1, the regression coefficient, as its estimate, and the exponent of that beta 1 estimate is the odds ratio, because this is a categorical variable. If this categorical variable is true for an individual, the odds ratio multiplied by the baseline odds gives you the odds of the outcome in that patient. Now, obviously, we can extend this model with multiple other variables, and what is most interesting is to look at the effects of continuous variables, such as variable 3 in this model. Variable 3 gives us the log odds ratio 3 as its estimate of the regression coefficient beta 3. And if we take the exponent of that, we get the odds ratio 3. And if we want to calculate the odds of the disease for an individual with a known value of continuous variable 3x3, we have to multiply the baseline odds with at least the product of the odds ratio times the value of x3. Or in other words, continuous variable 3 increases the odds of the disease with a factor odds ratio 3 relative to the baseline odds per unit of increase in x3. But because this is a multivariable model, we also need to account for the contributions of categorical variable 1 and 2. So only if these two categorical variables are untrue and have the value 0, then we already have arrived at the odds estimate of that particular individual. But if they are true, then we also need to incorporate the effects of these variables, if they are true, by multiplying with their respective odds ratio. Alright, that's a wrap for Modeling Basics Logistic Regression. By now you have already developed a good understanding of the basics of regression models, probably better than most medical researchers. But we will continue with different models in the upcoming lessons, and the next stop is Poisson regression.